I can't remember if we're going to finish up the slides this time or not. Let's see. I think, nice, we will, cool. So, okay, pointers. They are a variable that lets us hold the address of another variable. It gets very complicated because types are involved when you make pointers. But we've learned, we see what things are happening. We know what references are doing for us now, secretly what's going on. Let's see if we remember the syntax. All right, so let's do number 1. You can help each other. But let's go to the by-clicker page after you say that you're here. Let me ask you a question. 2 questions. So you can do both together right now, and then we'll just enter in the first one. If I use the star in the type of a variable, what does it mean? One of these 3. And then if I use a star somewhere outside of a type name, when I'm not making a variable, brand new, what does it mean then? Because it's overloaded, isn't it? So answer in number 1 on the website, please, but think of the answer to both so you'll be ready for the second one. All right? Any questions about the question? All right. Go off and do that. Give you a couple minutes. But just enter in the first answer right now. All right, so as hints, here's what I mean by in a type and outside of a type, right? Do we know what that is? Whee! So here we have int star p, for example, equals something. This is the use of the star in a type name. What does that mean? And then, like, outside of a type, like star p equals star p plus 1. Those are two uses of p outside of a type. Yeah? Two uses of the star. All right, so let's take a look at what we're thinking. Get your answers in. Your best guess. I feel like there's more than 8 of us in this room. I'm a little concerned. Have we all lost our passwords? But we're thinking A. A is exactly what it means. And when you're making a brand new variable, you say int star p, that means that p is a pointer to an int. Good. That's the A. And then let's do number 2 just quickly, since you're already on the page, I hope. What does number 2 mean? If you use it outside of a type, what is that operation doing? What do we call it? I'll give you a few seconds, 5 more seconds to do it. Alright. So, I'm concerned about the lack of responses. Have we just forgotten? Or what? You gotta tell me. And we're conflicted about the answer too, so maybe we just don't remember. So let's talk about it. When you use the star outside of a type, it means dereference. We're following the pointer. It's called the dereference operation. So it is C. B, address of, that one was not one of the answers. What is the address of operation? What's the operator for that one? That's the ampersand. Good. So that's when you have, like, I have an int variable laying around somewhere, and I would like to initialize my pointer p to hold the address of x. That's the ampersand. Address of x. That's how you read it. And we already know that the ampersand is overloaded, right? If you use the ampersand in a type, that means reference. That's fun. So yeah, that would be the third option. That would be address of. Okay, any questions about that? Please tell me if you're confused, otherwise I do not know. Alright. Let us keep on trucking. I have a new concept for us. It is called the heap. It is a magical place And a lot of cool things happen there. This is going to be where you live, more or less, in CSCI 41. So it's important to learn about it. It's a place where you can control how memory gets made and when it goes away, too, which is kind of cool. And so, yeah, let's make some variables that live forever in a new way. All right. So remember what global variables are. That's one way to make this happen. If you make a global variable, like here's main. If you make variables outside of any function, including main, they are global variables. They live for the life of the program, right? So like not in here, but like up here. Here's an int global variable. That lives forever, and its memory lasts for the life of the program, because who knows who's going to need it. And an issue arises if you say, like, maybe you make an array that's a global array, and R that's of size, I don't know, 1 million, something giant that uses up a lot of memory. This would be a global variable again, and it would live for the life of the program. And maybe, though, you only need that array for the first half of the program. You might run out of memory in the second half if you need more things, huh? So that's a bit of an issue. What if I need a lot of space for everybody to use, but I don't want to have it forever? I want to get rid of that memory sometime later, okay? So global variables cannot do that for you. Global variables are allocated. That's a word that means made in memory. They're allocated right when that program begins its life. And they last forever because anybody has access to them. They can use them until the end of the program. So that is their downside as well as their upside, right? They live forever, and maybe you only need that array for the first half of the program, and you're wasting space for every other program running on your computer or for your current program for the rest of that life of it, okay? Does that make enough sense? The globals are great. They let us access memory everywhere, but we can't, like, tell the array to go away once we're done with it. It stays. Global variables stay forever, okay? So there's a secret new place called the heap where you have that kind of control. All right. So this is why I'm teaching it to you. So first we have to talk about how your memory looks when you load a program. When you say / run my program, or you double click something on your Windows computer or whatever. Here's what's going on inside of memory. All right. So your program is going to get loaded into memory, and here's what it looks like. There's a bunch of different sections to your program. There is a text section. These are all historical names, and this is where the code lives. All right, so here's low addresses down here, and here's high addresses up here. So it's taking up all this space from here to here, your entire program. And like the text section is the machine code for your program. It's like the int main. It's the body of all your functions. That's your instructions. Those have to live in memory too somewhere. Your code, and then there's a separate spot in memory just for your global variable. So you make an int, that's where it lives. There's a separate spot in memory for that giant array. Since they have to live forever, you need space allocated for them the second the program starts. So it's the global data section. That's where that lives. And then there's a third part. There's a third piece of memory that your program has, and it's made up of two pieces. All right. There's a third section made up of two pieces, and they share that spot. They share that chunk. All right. The first spot is your function call stack, which you understand. You know that one already. That's where all your local variables live, and it's going to grow down towards low addresses, address 0. So like here is, I don't know, here's like your main function call, and then like main calls foo, and then these all have local variables. And then foo calls bar or something. And so like the stack, it grows and shrinks as you call it functions and as they return. Like bar has some local variables, and then it returns and it goes back to foo. Okay? So that's the stack. It lives in memory. We know that. It shares space with this thing called the heap, this new idea called the heap. All right? The heap is a place that holds dynamically allocated data. All right? It's stuff that you can say, I would like a bunch of stuff. It's a place where you can allocate memory. Like, I would like some memory, please, C++. And then it lasts for as long as you want it to last. Like, make me an array. Make me an int on the heap. Make me an array on the heap. And then you could come along later and say, I'm done with this thing. You can have it back, memory. That's what the heap can do. Okay, that's the new thing. You can get rid of stuff from the heap, all right? But it's fighting for space with the stack, and it's growing upwards towards the higher addresses. So like, give me another int heap, give me another array heap, give me a double this time, things like that. It's growing down while the stack's, it's growing up, I guess, while the stack's growing down. And if these two ends ever meet, like you ask for some stuff on the heap, and that like tries to bleed into a stack frame, or you try to call another function and that bleeds into like some array that you allocated on the heap, should the two pieces, should these two dotted lines ever cross each other, that's when your program runs out of memory. Okay? And you will get a runtime error. The program will end itself because that's you can't do anything other than give up at that point. Okay? But that is the new place. You have your text section, which is your code, global data for global memory, global variables, stack section for the function call stack and all the local variables that are used, and then this new place called the heap that holds dynamically allocated stuff that you say, I want this memory now, and I can delete it later. It can be reclaimed. That's fighting for space with the stack. Okay, any questions about any of that? Interesting idea. Maybe we forgot that our code is in memory too. That's an odd thing to think about, but it must go there. But let's zoom in on the heap now. What is that good for? It's made for when you would like to make memory and have it live for just as long as you'd like it to live, but it can live between function calls too. It's like a global variable, but it's potentially temporary. All right? So like global variables, heap memory can live forever, and unlike globals though, you can delete, you can reclaim that memory. All right? And as the program's running, you can say how much you want. Like you can get a number from the user, cnn, and this is another nice thing about the heap. Like maybe the user types 42 or they type 42 million. You can use that number, the thing that you're getting as the program's running, to allocate memory. You can be like, all right, I'm going to make an array on the heap of that many things. I don't know ahead of time before I compile the program how many things I'll need, but here, I know now as the program's running. So you can make a giant array on the heap, and then you can get rid of it. You can get rid of it later. All right, that's the goal. So let's see here. If that makes enough sense, it's a weird new concept. It's just memory you can get rid of when you ask it to. Let's learn how to ask. Let's learn how to ask for memory and learn how to ask for it to be gotten rid of. There's two new operators to learn. The first one is called new, which is kind of fun. So the new operator, it gives you back a pointer to something that it makes for you on the heap. Okay? So let me draw some pictures. This is how you use it. You say new, and then you say the type of thing that you would like made for you on the heap, because that's how C++ knows how many bytes to give you. So it's like new int, so make me 4 bytes on the heap, please. If you say new int, it will give back, this will result in a pointer to that integer that got made for you on the heap. All right, so this is the kind of line that you would say. You'd be like, all right, give me a new int and store that address, because you're getting back an address of the thing on the heap. Store back that address in an int star. And then you can go into that int that got made for you on the heap by dereferencing that pointer. All right, so let's draw what happens when this line gets run right here. So here's the stack. Your local variables live on the stack. Anything with a name lives on the stack. So n's a stack variable. It's a local variable. The address of something on the heap. So when you say int star n equals new int, first this happens, new int. That makes a brand new box in memory on the heap that's capable of holding an int. It's shiny and new. Sparkling. All right? And it has an address. It has some address, maybe 100. And by default, it's set to garbage as usual. And then n is being, it's getting that address. It's getting 100, and it's pointing just like that. And then you can say, you can go through n to set this heap memory. Okay? That's the idea. Any questions about that? So you say new, and you give the type name, and you're getting back a pointer to that type on the heap. That's why we had to learn about pointers first. We just made memory, and it can last forever until we tell it to be deleted. Okay? Does that make enough sense so far? I'll go to code in just a slide, I think. But let's talk about how to get rid of stuff now. The whole power of the heap is that you can remove memory that you make, and it's called the delete operator. So every new should have a corresponding delete. Right? That gets rid of memory at some address on the heap. You say delete, and then you give a pointer. You give the address of somewhere on the heap that we would like to get rid of. So like if we had this, copy, paste. So if this existed and n was a pointer to somewhere on the heap, if we say delete n, that would go into memory and delete this thing. All right? And then that memory got reclaimed. It can be reused for things. Now you should not go through n anymore. It's undefined behavior to go through n because it's pointing to some address that has been reclaimed. It doesn't exist anymore. So there's some things to watch out for, but that's the setup. You say new when you want something made, and delete when you like to get rid of it. And it lives for the life of the program until you say delete. So it's like a more powerful global variable. Does that idea make enough sense to us? New and delete. All right, so reclaim. That is the beauty of all this stuff. So let's have an example, and I'll try to show you what's going on here. Heap.cpp. So I would like, let's see. I want to say something like int star n equals new int. And what this line does is it makes room, makes space for one int on the heap. And it saves the address of that thing that got made into the n variable. Save the address of it into n. Okay, so that's what that line does. And then you can go through n and set it. Be like star n equals 42, cout star n. You can use it as much as you want. And once you're done with it, you say delete. Once you're done with heap memory, oops, you delete it. It's good practice. Even if it's right before your program ends, even though that memory is going to get reclaimed always when your program ends, it's good practice to remember to delete your heap memory. So here's like the allocation. Here's like me using the thing, and then once I'm done with it, delete n, and I can put a bunch more code down here and reuse that memory potentially. C++, heap.cpp-o heap. This is a very complicated way to print 42. But I promise this is useful. Alright, so any questions about this so far before I make it a fancier program that maybe looks a bit more like the one you might write? One that you'd want to use the heap for. Because this is kind of useless, right? Just making an int. You could just have made a normal int variable and have it hold a 42, right? The magic of the heap is that you can make that memory somewhere, and you can just keep passing it around, and everybody gets it. All right. So instead of all this, let me, I don't know, let's say this. Let's be like int star p equals a function call. Make a new int on the heap. So this is where it gets a little more powerful. And then in that function, it has to return something. It has to return an int star. Make new int on the heap. Well, let's copy all this. Be like, okay, there you go. So this is a bit cooler. Return n. Look at what I can do. And now it's got to be delete p, since that's what I'm calling it. I can call a function. It can create memory, right? Making something on the heap. And this address is fine after this function returns. It's made on the heap. It's somewhere global. I can always have it. So I'm giving back that address. And now I can get to the same place through p in main. So this is weird, right? This is a function above returning something to a function below that it made on the heap, and me being able to use it still. That's magical. All right, that might not make a lot of sense right now, but that is something we have not been able to do yet. Because usually when functions return, all of their memory goes away. But no, we made that box on the heap. It lives. It's still alive. And so we can return that address and keep messing with it. We can call it p down here. We can be like star p equals star p plus 1. Use it as much as we want. As long as we have that address somewhere. And be like cout star p. As long as we have that address somewhere, we can keep messing with that box on the heap, that int, all right? And then we can delete it, as long as we have some way to get at it. So that's where it gets a bit cooler, I think. Alright, so here I am making a new int on the heap, which is making it up here, messing with it, printing it out, giving back its address, and that is still a valid address to touch because it was made on the heap. It lives until you say delete. In between function calls even. Isn't that fun? So, I like that. Any questions about that? It's a new fun idea. Alright. Definitely a little bit more of a difficult concept though, just like pointers. So, if we are happy enough with that, let's talk about, let me share a secret with you. Dun, dun, dun. If you make an array and you use an array, you're actually secretly using pointers this whole time. It's kind of weird to think about, but here's what I've been drawing, right? If you make an array of 42 things, let's go back to blue. If you make an array of 42 things, I've been drawing it like this, but secretly that was incorrect, right? It's good to teach it to you, though. It's good to think of it like this. Like here's, you can set values, 1, 2, 3, blah, blah, blah. Assume there's 42 elements, though. I've been drawing it like this. That's R. But secretly, R is a pointer to the beginning of that array. So secretly, like this is index 0, 1, and 2. You think of them as addresses. This is like address 100. This is address 104, 108. And R, just by itself, is a pointer to the first element of the array. So address 100. Let me prove that to you. That's a little weird. I promise that's a thing. Let's see. I can be done with all this, can't I? There we go. Let's do arrays.cpp. Dun, dun, dun. So int R equals, let's make an array of like 3 things, I don't know. And then watch. You never tried this, but it's a thing. I'll print out just R without saying any brackets or anything. Took a while. That is an address. Crazy. And of course, there'll be a different one every time I run the program. But R by itself is just an address. It's the address of the first element of that array. And we can confirm that, right? With what's the first element of the array? R of 0. What's its address? These are the same. They are legitimately equivalent ways of saying the same thing. They print the same address. They are the same place, all right? So what does that mean? What does that mean, right? I have 2 ways to print the 5 now, don't I? So I have 2 ways to get at its address. The first way to print the 5 is, of course, saying cout R of 0, right? But what's that but just like dereferencing this address? So if I have another address that gets me there, just R by itself, another way to print 5 would be to say star R, because that's the address of the 5, of the 0th element. So those are 2 equally valid ways of printing 5. So this says that R is the address of R0, and that means star R is R of 0, just like that gets rid of the address of, right? It dereferences. How cool is that, right? So, all right, this is what's been going on. Secretly, this syntax with these brackets, that is being translated into this syntax with pointers and dereferences, all right? So secretly, this is doing nothing for you. It's just pointers at the end of the day. And so that means, what is the pointer-like equivalent of accessing like element number 1 of the array, right? What does that get translated into? More secrets time, right? If you ask for any index of an array, what it's doing is it's going to offset the address. It's going to do what's called pointer arithmetic. It's going to add 1 to R and then dereference that. That's all the syntax is. That's what it's getting compiled into, right? Secretly. So like if this is your array, we had our 5, 6, 7. Maybe this lives at address 10, this is 14, this is 18. If you say R, R is giving you address 10, but R plus 1 is not giving you address 11 like you might think. R plus 1. That's giving you address 14, because C++ is nice, all right? So first of all, R is the starting address of the array. 1 is supposed to be an offset into it, but C++ knows because R is an int pointer, you must want one int leader rather than one byte leader. You'd like to stay in int land, most likely. And so it knows to get, even though you say plus 1, it's going to give you address 14. It's the address of the next int. It's trying to be nice to you, okay? So that's kind of cool. That's called pointer arithmetic. It will calculate the address. So R plus 1 is the address of index 1 in this array. And if you dereference that, that will get you the value at index 1. Does that make enough sense? It's a little weird. It's called pointer arithmetic. So that is two competing ways to get the 6. Secretly, the first way is being translated into the second way. This is equivalent to R of 1. Crazy, all right? Let's see, what else could we do with this? Well, if the first element, if you just say R, that's a pointer to the first element, that means R's type is an int star, first of all. So I can do this too. If it's just an int star, I can save it somewhere else. I can be like int star p equals R. That's valid. Does that make sense? Because R is just a pointer to the first element. Its type must be int star. And then, because this could be a pointer to an array, and this syntax is secretly this syntax, this should blow your minds. I can do this. P of 2 to an int star. Assuming it really is an array on the other end, that will do P plus 2 and dereference it. And that will really give me a 7. So I'm going through a pointer. I'm treating it like an array. That's possible. Now with all that we know. All right? So this is going to do what? P plus 2 and then dereference it. Cool. Okay. Are there any questions about that? That's a lot. New knowledge. Secret knowledge that we didn't know before about arrays. Does that make enough sense to move on? Alright. So, you can also do this for C strings. This is why it's char star. Now you know, right? So you can do this for C strings as well, since those are just character arrays, right? That's all a C string was. It's a character array with a null terminator at the end. So now you know why people say, and all the C library documentation says char star instead of like char brackets, right? Because those are equivalent types. So technically, now you know why this is a thing. Char star argv bracket. But actually, since any array is equivalent to a star, this whole type is equivalent to char star argv, isn't it? A pointer to C strings, because that's all an array is. It's a pointer to the first C string. That's all the argv array is. So that might be melting our minds a little too much. You don't have to worry about that. But this is the idea, at least. All right? Yeah, I think that's what I wanted to say about that. So arrays, kind of cool. You can treat them like pointers. And that's great, because what you get back from new is always a pointer to something. So you can make arrays on the heap, and the syntax looks a bit weird, but now we kind of are going to understand it, since we know what arrays are doing. So you can make arrays on the heap and delete them. Here is the syntax for that. You say new int, and then you put brackets how big you want the array of ints. And that'll do that. That will create the array of ints on the heap. And then what you are getting back always from new is the starting address, all right? But you know that's okay. You have to put it in a pointer, but you can use it like an array. You know that syntax works now. Stack, heap. So here's what's going on when you run this line. First you say new int 42, and so that makes a brand new array on the heap of size 42. Maybe the very first element is address 100, and it's shiny and new. Brand new memory, fresh. And then what you're getting back from that call to new is the address of where that got made. And you can place that somewhere. You should place that somewhere, otherwise you forgot about it. So you're placing that in P, which is a local variable, has a name. That's getting your 100, and that's how you will interact with this array. Now you can say P of 0 equals 42, because you know that syntax will work with an array, even if it's saved as an int star. Okay, that's the goal. And so that'll put 42 right there. That's what we want. Okay. When you're done using your array that you made on the heap, you have to say delete as usual, but you have to say delete with brackets. Delete bracket bracket P, because C++ can't tell, was this thing that you're deleting, was it just a single int? Because it's still a pointer, right? It's always a pointer to the first thing or a pointer to the whole thing. Was it a single int or was it an array of ints? Do you want me to delete stuff after this too? And we do. So you remind C++, no, I made an array, not just a single int on the heap. I made an array, delete the whole thing, please. You say delete bracket bracket, okay? That is the syntax, and that will go away and remove it. Question? That's a very good question. So secretly in the heap, it's keeping track of, like, there's an arrangement to this memory. It's keeping track of some metadata about stuff that got allocated. It's like, all right, this thing that starts at this address, it has this length and number of bytes. It's saving that information secretly somewhere, but we don't have access to it. That's a good question. So you can technically, it's called an allocator. You can make your own allocator. You can make just a giant array of bytes, and you could pretend that's the heap, and you can start allocating from it. You might have to do that one day in an operating systems class. So that is a very fun idea. That's a great question. Any other questions? The heap knows, it remembers, but we don't get to know how it's doing it, sadly. Because there are competing implementations for the new operator. Let's see here. So yeah, with that in mind, here's an example of that. I've already used P, so let's say Q instead. You'd be like int star Q equals, let's make a new array, a new array of ints on the heap, have it hold size 42. So what this line does, right, is Q holds now the address of the first element in this size 42 array that we just made on the heap. That's what's going on. That's what's happening there. And you can mess with it just like a normal array. You can be like Q of 5 equals 55. Cool. And then you can see out the fruits of your labor. And then once you're done with it, you delete it. You say delete, and it's an array, so you say delete bracket bracket Q. And so that'll print 55. And I'm reclaiming that memory with the line, with this delete bracket bracket line, okay? So remember that bracket brackets for an array on the heap. Alright, so yeah, I think that's what I wanted to show you there. Does that make enough sense? Any questions about that? Because I have a question for you now. Let's go to it. So here are 3 lines of code. All right. It's your turn to do what I've been doing. I would like you to draw the state of memory. What does the memory look like after these 3 lines have finished executing? So some things are being made on the stack, right? Local variables. Some things are being made on the heap. They're being allocated on the fly. So figure out what's where. And then, once you're done with that, draw what happens if you say delete P. So here's P. What would happen? Which box/boxes would you draw a slash through? Which memory would be reclaimed if you said delete P? Just like that. Okay? So those are your 2 questions. Are there any questions about the question? This is a complicated example, but it's great practice. So give that a try. Just take out a piece of paper. Help your neighbors, please. And then I'll show you how I think about it. You don't have to write it down anywhere though. Just for you. So how many boxes are getting made? Where? Just the thing called P. Based on what we know. What are you going to draw a /3? So come up with a best guess, because this is also gonna help you understand what you don't know once I explain it to you. So give it a try. It's worth it. Another 30 seconds to write down your idea. This is good practice, though. Come back to this. So int star is a type. It's a valid type. Alright, that's my timer. Did any questions come up as we were trying this that would not be answered by me solving it? Alright, so first line looks a little weird, but it makes sense given what we know, right? We say new, and we provide a type of thing we'd like. We'd like a box that holds this type on the heap, please. Alright, so it's just a box that it's capable of holding an int star. That's all it is. So here's heap memory that just got made. Maybe it's address, I don't know, 100. And it's of type int star. Alright, I'll draw a circle around it. That's the type of this box. Does that make sense? New int star makes you a new int star box on the heap, just like new int made you a box that holds a single int on the heap. So that's that. The syntax looks a little weird, though. I'll give you that. And then you're getting back a pointer to that place that got made for you, so naturally you must put that in a pointer to an int star, because that's its type. And that's P. P has a name. Things with names live on the stack. So this is P, the one and only stack variable in this example. Did we get that? So P is of type int star star. It's a pointer to an int pointer. It's got to hold the address of this guy, which is an int star. So it's holding 100. And it's pointing just like that. Okay? That's the idea. That's what P is doing. Any questions about that line? That's the first line. So the type of this is int star star. It's giving you back the address of that int star that it made. Right? We're ready for the second line? This is saying star P equals new int. So it's always the right side that gets executed first. So this one's actually making an int on the heap. So we say new int. That makes a brand new box that holds an int on the heap. Its type is int. And it's giving you back an int star. It's giving you back a pointer to that place that it made for you. So maybe this is address 200. And it's storing that in star P. This is where it gets a little weird. What's star P? It's not this. This is P. Star P is dereferencing P and talking about this box. And do you see how the types align? It's perfect. Because this is an int star. This could hold the address of an int. Perfect. That's the 200. That's where we're placing it. Does that make sense? And then this is pointing there. Therefore. You see that? Questions about the second line? And then finally, star P equals 42. It's like, all right, star P gives me here. Star that one more time gives me here. Set that to 42. Boop. So that's step 1. That's the answer to question 1. Does that make enough sense? The types are important to keep track of, I would say. So that's what's going on there. And then when we say delete P, what will be deleted? Which box? This box, this box, this box, maybe multiple? Well, going back to the first example of deletion, it's always you give an address, and the thing at that address on the heap is going to have a slash drawn through it. That's what's going to be reclaimed. So if you say delete P, P is an address to something on the heap. It's address 100. It's saying delete the thing at address 100. It's deleting this. Does that make sense? It is not also deleting this. So it was a mistake to do this. Because now I have lost this int on the heap. I have no way of getting at it anymore. So that was a bit of a mistake, but this is the box that's going away. This is the memory that's being reclaimed. I can't go through it anymore. So that's what delete P will do in green. Any questions about that? This is a good example. Try and erase cover up my answer and try to do it yourself again if you got it wrong. Hopefully, it's making a little bit more sense now that I've done it, okay? But if we're good, there's a name for what we just did, for this delete P, and we forgot about this guy. That's called a memory leak, so we should talk about that, because that's a very common error once you have heap stuff involved, all right? So a memory leak is when you had data that you made on the heap, and you lost access to it. And it's memory it's in use, it's taking up space, but you have no way of getting at it anymore. You've leaked it. You have no way of accessing it. It's called a memory leak. So here's the world's simplest example of that. Let me draw what's going on in this example. So you're saying int star I equals new int. We know what that means now. It's like I is a variable. It's capable of holding the address of an int. And here's the new int that we just made for ourselves on the heap. So it makes a new int, gets back the address to it, and then it saves that address in I. So maybe this is our favorite address, 100. So I holds 100 after that first line. So it's pointing like that. And then you can be like star I equals 42, sure. Set the box, 42. And then if you come along and say I equals new int again, that's going to make a new box, right? New int always makes a brand new box in the heap, if there's memory available at least. Usually there will be. So new int makes a new box, and we just set I to the thing that new int gave back, which was the address of that box. Maybe this is address 200. So we just did this. I is holding 200 now. So now we chopped off this link, because I is holding address 200, and we're pointing to here now. Boop. And we can set that to 43. Do we see that we don't remember the address of the first int anymore? We have no means of getting at it. We can't. There's no hard-coded place that it could be. The heap is just giving you a memory address somewhere. We have no control over where, so we can't even guess where it is. We have lost access to that first int. This 42, it's lost. It's taking up memory for the rest of the program, but we don't get to use it. We've leaked memory. It's useless memory at this point, okay? So this line is where it all goes wrong. Do we see that? Any questions about a memory leak? So you've lost this memory. It's going to exist because heap memory lives forever until you say delete. We've lost the address to use delete on. That's no fun. And so programs that leak memory, think of old programs, like an old web browser or something. Eventually programs crash, right? Because they run out of memory, usually because they keep allocating memory and they have a leak somewhere, so they can't deallocate the old stuff, all of it. That's why they crash and run out of memory. So that's fun. Fun little idea, I think. We good with that? All right. So, here is like a full-blown example of using the heap. Let's do something real now. Let's do this. Let's ask the user for some number. They'll give us a number n, let's say. And we're going to make an array of size n on the heap. Maybe it's 1,000,000, maybe it's 42. We don't know. And then we'll ask the user what they want to put in that array. We'll ask them for n things. Give those to me, please. And then maybe we'll calculate the sum of the array, and then once we're done with it, we'll delete it. All right? We'll try and talk about the lifetime of that memory. So that is going to be the goal for this example, something that you might actually do with the heap. Some normal sounding example. So we'll call this array sum.cpp. So, int n, we're going to ask the user, hey, how big of an array would you like? Enter the array size. Boop. And then cnn. And then we want to make that sized array on the heap. We say make an array of n ints on the heap. And the syntax for that is we say new int of size n. N is in brackets. That's totally fine. So, and that's going to go in int star, right? You're always going to get a pointer to the first thing, and you can use that like an array if you'd like. That's perfect. Right? So that's making it, and now we can fill it. Just ask the user for n things. So for int I equals 0, first index, I is less than n, last index. There, I is less than n, I plus plus. So it goes up to n minus 1, which is the last valid index of that array r. And then we'll get it. We'll be like int next elim. We'll see out, enter the next element. And we'll get that from the user with the cn. And then we'll put that in r of I. So now we're filling this array that we made on the heap. Cool. And then maybe you can imagine like this is all being passed around between functions because it's heap memory. You can do that. But we're just doing it in main to keep it simple. Now we want to sum it all up. Sum everything. And so like the sum variable starts at 0, and I don't want to visit every index now. This is a bit of a contrived example, but you get the idea. So for every index in R, let's add it into the sum variable. There. And then we want to output the sum. See out sum. That's the work that we set out to do. All right. So we make this thing on the heap. We fill it, and then we use it to calculate some sum or whatever we care about. All right, and we see out sum. So now my question for you is, where in the program do I not need the array anymore? Because like I can say delete down here, but this is kind of I could have done it earlier. Delete bracket bracket r. Where could I move this to? Where's the earliest that I could delete the array? When am I really done with it? Well, I'm accessing it in this loop, so I definitely can't move it above the loop. But I can put it above the cout line. See that? This is where I'm done with the array at this point. I'm just going to cout sum for the rest of the program. So this is where I don't need that memory anymore. You always want to figure out, when am I done with this thing? Done with R. Delete it. That's the idea. All right, let's put this on a line above, actually. Better. So that's my better example, I would say. So let's see if I can split screen this. So we get a number from the user, make an array of that size on the heap, use that array just like a normal array, fill it, sum stuff, output the sum, but then remember to reclaim that memory once we're done using it. That's our new job now that we have this power. Okay? And so let's, I don't know, well, let's run it. Oops, sorry, array sum is its name. And so array size 5, 1, 2, 3, 4, 5. Apparently there's 15 things there. And so that made a size 5 array on the heap and reclaimed it. And then if I do 10, it'll make a size 10 array on the heap. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And apparently that sums 55. So that's a good use case of arrays, I would say, on the heap. You can imagine this could get much fancier. You could be passing along this address between function calls, but it lives until you're done with it. Because maybe you want to make you want to ask the user to enter another array after this. You can reuse that memory if you use the heap. Isn't that beautiful? Any questions about that? So let me spell that out, actually. That's a good idea. Now I could ask the user for another array and reuse the first array's memory. So you'll never run out of space if you do it like that, maybe. That's great. All right. Let's see, do I want to write a program about that? I do not. Okay. So, first of all, when you're using vectors and when you're using strings, those are secretly using heap arrays, okay? There's a reason you're learning about this. Vectors and strings, they're secretly using either arrays of characters or arrays of like ints or whatever your vector type is deep down. And that's how you can add more things and add more things. It's like resizing that heap array in a certain way. So it's good to understand that. So that's why we're learning about it. And then also in CSCI 41, at least in my class, I'm going to have you implement a vector. And you're going to have to use the heap and dynamically allocated arrays and deletion and all that fun stuff. You need to learn what it means to be a vector in that class, at least. Yeah, it's a very common thing to ask students to implement in a CSCI 41 class. Good. So, yeah, that is the point to all of this. This is why you're learning a bit about it, so you can understand how to implement your own data structures. This is a very common thing to need to be able to do. It's managing memory. All right? Any questions about anything we just talked about? So the heap. It's a bit complicated, I would say, just like everything else in these pointer slides, but it's very useful. It's used everywhere. Okay? One day you're going to need to know it. Are we good to move on? Because I want to show you something, another CSCI 41 topic that I'm not going to test you on, but you will be reading about in your book. I think you might have a Xylab about it too, but not a class server lab. It's called linked lists. This is the greatest possible use case of heap memory and pointers that I could possibly give you at this point, but it's a CSCI 41 concept. All right, so I'm not going to test you on this, but this is the best answer I can give you right now. The best answer many people could possibly ever give you about like when would you ever want to use a pointer over a reference, since references are better, easier to use. Linked lists are the answer. And what's a good reason to use the heap? Linked lists are the answer. All right, so let me try and teach you them at a CSCI 40 level. I'm not going to test you on this. All right, you're going to learn so much about this in CSCI 41. Just wait. So what a linked list is, it's a data structure that's a competitor to an array or a vector. All right, it's made up of a chain of things. So like instead of storing an array 1, 2, 3. It's made up of a chain of what we call nodes. So we can make a linked list that holds 1, 2, and 3 in that order. And here's how you do it. You would have, like on the stack, you'd have a pointer to where your list begins. And then on the heap, you'd place all of your nodes that hold a piece of data, like 1, and then the address of the next node in the list. So it's like a little chain on like a bracelet that you can follow down. There's the 2 node, and it knows how to get to the 3 node, and the 3 node knows that's the end of the list, so you put like the null address there, 0, and I'll draw a slash. That is what a linked list is. It's like you can represent the idea of 1, then 2, then 3 in order with some data and a next pointer, some data and a next pointer, some data and a next pointer, right? So that's a bit complicated. You'll read about it in your book. I'm not going to test you on it, like I said. But most of the time, these nodes are made on the heap because you have no clue how many you need up front. Like I would like to have a list of 50 things versus a list of 500 things. Just make everything on the heap one by one. That's fine. And these are a linked list is a competitor to arrays and vectors. There are some things that are very easy to do with linked lists that are very hard to do with vectors. Like adding something to the beginning of an existing vector, like putting a 0 here, that's disgustingly hard, isn't it? You'd have to be like, all right, let's push back the 0, and then let's just shuffle everybody around. You got to move things, because index 0 is right here. You can't like put something before it. You can add to the end of a vector easily, but you can't add to the start of a vector easily. A linked list is just like, all right, 0 node, put a pointer there, change this pointer, you're done. So some things are easier with linked lists, and you will learn plenty about that in the future. All right? But that is the greatest example of both the heap and pointers that I could possibly give you, so hopefully it makes at least a little bit of sense. All right? This is why you want to learn these things, so you can make data structures. All right? So here's that example again. So if you have an array or a vector, assume that there's room, or you just want to call pushback. Let's say you want to change this, you want to add 0 to the start, and you have a room. You have a room for a 0, but you want to put it at the start of this array. So what you are forced to do in an array, if you want to put something at the beginning and you have room for it, you better shuffle everybody. Like 3 goes here now. 2 needs to move down to here. And then, let's see. Then the 1 needs to move over here. 1 goes there, and then you put a 0 here. So now it's 0, 1, 2, 3. You have to touch the entire array. So if this was a size 1 million array, you have to visit every index of that size 1 million array to put something at the front. So that's disgusting, all right? A linked list is good at this. Regardless of if you had a size 1 million linked list, doesn't matter. So this is like, here's 1, 2, 3, the existing list. 2, I don't know, 3 goes in order like that. I'm drawing nodes in this way. If I would like to add, right now the list is pointing to this guy, that's the start of it. To add a 0 at the beginning, all I need to do is make a new node on the heap, put 0 in it, have the next pointer, because that's how it knows to get to the next place, have it point to the old start of the list, and then chop this guy off and say the 0 pointer is the start of the list now. That's it. So that was simple, and it doesn't matter how big the list was. It's great. So how would you make each of these nodes? Those are just structs. Struct node, what does it hold? It holds 2 pieces, right? It holds data, like an int, and then it holds the address of the next node in the list. So this is a little weird looking. It's node star next. That's a great use of pointers. You're forced to use pointers here. You can't use references. So that's a great example of that, plus the heap. And it is a little weird. This is called a recursive type. This is, you're defining the struct node with nodes inside of itself. Crazy. But the pointers kind of break the infinity of it all. It's really cool to think about and study. If this excites you at all, you're going to love CSCI 41. All right? But I won't test you on this. It's weird, but it's the answer to probably all of your burning questions. Why in the world do I care about pointers? When would I need them? Why in the world do I care about heaps? When do I need to use that? This is a good example. All right. Any questions before I move on to one last thing that's going to save your life in future labs that involve pointers? All right, because you know you're going to mess up, right? You know you're going to have seg faults all day long. You're going to have runtime errors, and you're going to be very confused, right, when you use pointers in the heap, and I'm going to force you to, of course, because that's what we're learning. There's a thing called GDB, and it's going to help you immensely. It will save your life just like that C++ tutor website saved your life back in the day when I showed you that when you were first learning about C++. So GDB, greatest thing ever for right now. It stands for the GNU debugger. It's made by the same people who made our C++ compiler. G++ stands for the GNU C++ compiler. So GDB is made by the same people, and it is just a program that runs your program. It's called a debugger. It helps you debug it, right? So it's a program that gives you helpful information about your program as it runs. It is able to hook into and inspect the values of variables, the line numbers where errors happen, even if they're runtime errors, because it's running inside of GDB, it remembers where it was. Even after a runtime error, you can inspect the values of variables that may have caused the problem. It's amazing. So the only thing you have to remember to use GDB is you have to compile with -g. There's a flag called -g, G for GDB, I guess. That adds like little debugging information to your file, little bits of metadata that say like, oh, this machine code corresponds to this line number, this address corresponds to this variable in the program, etc., etc. So normally you compile like this, G++, name of the file, -o, output, right? just add a -G here at the start, and that will allow you to use GDB. Okay, so let me show you an example of how powerful and wonderful this thing called GDB is. You're going to compile with that -G flag, and here's just a program with an error. Let's say segfault.cpp. Program with the seg fault. Let's have it at least be a little interesting. So here's a function call. It'll be called void And what happens in the function? Well, we say int x equals 42, and then int star p equals null pointer. Maybe it should have been the address of x, I don't know. Cout star p. So this is going to blow up, right? This is going to dereference null, which is an address we cannot access. Doesn't exist, the 0 address. And so if you run it, you're like, oh, apparently there is a problem, right? Just imagine you're working on a lab and something like this happens. It's going to be much more subtle, right? But you got a seg fault and you're trying to figure out why. You could totally print out variable values all day long like you've been doing to debug, but there's a quicker way, and that's using GDB. So here's what you do. You're going to compile this program with a -G, which doesn't really change much. Like it still is a program that is runnable. But now we have debugging information in that file. It'll still segfault, of course, but now we can load it into GDB, right? So instead of just running it by itself, instead of saying /segfault, just tack a GDB at the start of that. GDB is the name of a terminal command. So say not just /segfault, but say GDB./segfault. Just pretend to run it in GDB, hit enter, and it's a debugger, so it's got some output. Normally it won't show you this right now, but it wants me to press enter so it can show me all of its info. Keep pressing enter. And now I'm at the prompt for GDB. Okay? Now I'm inside of the debugger. So, here's what you say. You say R for run, or you can just type out run. R for run and hit enter to start running the program inside of GDB. Hit enter. And then look at this. Let's see if I can scroll this properly. It says segmentation fault in the function on line 7 of segfault.cpp, and oh, here's the line, if you wanted to see that immediately. Is that not the greatest thing ever? Do we see how this is going to save our lives? This is saying exactly where the problem was. So maybe you're using pointers all over your program. It's going to tell you the line number where the problem happened. I cannot stress how cool this is and how useful this is to you. Right? If that wasn't good enough, you can say BT, that's short for backtrace, that's a command, and that shows you the stack. If you're not sure how you came at how you got to this line, it's like, oh, okay, you started in main, and main called so you called on this line 11 of main. It was that particular call, maybe call it multiple times. It was that call, and then you were in and it was line 7 of that one that caused the problem. Great. That's the stack. That's showing how you came at this thing, which is great. You can move up or down the stack. I can show you that offline. You can also, it's still got the program loaded even though a runtime error happened. It can print the values of variables for you. And that's usually going to help you figure out what went wrong. So you can inspect every variable that exists right now. You can say print space, the name of the variable, right? It's another command to GDB, and that prints the value of that X variable in your current stack frame. You can move around between stack frames as well. But I'll have to show you that some other time. That's a bit more complicated. But you can be like, all right, has 2 variables. It's got X and it's got X and P. Let's print X. It's like, okay, yeah, X was 42. Okay, maybe that wasn't the problem. Okay, let's see what P was. Print P. Oh, P was holding the 0 address. I see. And then I was dereferencing it on line 7. That must have been the problem. Does that make sense? That's beautiful. That's the greatest thing ever. We love GDB. It'll be even more useful when you take CSCI 41. But GDB is great. Print the values of variables. When runtime errors occur, you're going to have a lot of runtime errors when you're writing pointer stuff. Okay? Once you're done with GDB, to get back to your terminal, you say quit or Q. Quit. It's like, do you want to end the program that I'm currently debugging? Be like, yes. Y for yes. And then you're back on the terminal. So I hope that has convinced you to try GDB when a seg fault happens. It's going to immediately give you the problem. It's great. Thanks Because usually it's either null dereference or it's like you're dereferencing a pointer that is like pointing to nowhere. Maybe it was garbage, something like that. So that's usually the other issue. But yeah, that's pretty much all I got for pointers in memory. If nothing else, now you can laugh at this joke, can't you? So now read it again and chuckle while I load or get ready to talk about the next thing. Yeah, I think that's right. Yay. Haha. We're ready. So, I'm glad pointers in memory. Let's see here. I don't know why I have that open. Let's go to Canvas. Oh, shoot. I think I clicked on something weird. That's what I did. It's this Canvas that I want to be on. Oh, and of course. Has the school turned on two-factor authentication for you guys, too? Not yet? Because this is such a pain. I guess it's good, like, nobody else can see your grades, but, like, it takes too long. Oh, really? You gotta be kidding me. Courses. See? That's just all silly. Alright, modules. We're getting there. We're getting there. I want to talk to you about your next midterm. If it loads. Alright, so, reminder. This is week 10. I promised you the second midterm during week 12, so that's 2 weeks away. So let's talk about it. Midterm 2 info, midterm 2 extra credit assignment. And so I'll publish this right now. And we'll talk about both of those. Nope. There. That one and that one. Alright, this is pretty much exactly the same as midterm 1, just new topics, right? So, midterm 2 will be in class on the 26th. That is the Thursday of the... Oh, man. I've lost a start menu. Is it back? There it is. 26th. Come on. Are you kidding me? There we go. All right. So here we are, Thursday of this week. 1 week after that, another week after that. That's the 26th. So we're in week 10 right now. Week 12, Thursday. That's the one. Okay? Well, that's when it'll be. And same time as before. Here are the topics. All these things. All these labs. I'll try and focus on these topics, but everything builds on top of itself in this class. You should, I don't know, be ready to write a loop or something. That's for sure. Yeah. Even though that was midterm 1 stuff, that's just going to be the rest of your computer science career, doing all that stuff. But those are the topics that I will pull heavily from, let's say. And then the format's exactly the same. Exact same format as the last midterm. Here's a sample one. That's the idea. Yeah. Any questions about, just read this, I guess. Any questions about the logistics or the topics or anything? Mostly straightforward, now that you've done the first one. And if we're good with that, there is an extra credit assignment with every midterm. So this is October 26th. Why is this? I guess I did it wrong, sorry. If the midterm's on the 26th, the extra credit assignment is due on the 25th at midnight. That's when I'll have it due, so let's fix that right now. 25th. 25th. There. Could have sworn that was correct before today, but never mind. So now, it's due the day before the midterm at midnight. It's worth up to 2.5% extra credit. It's the exact same extra credit as the first midterm. So make a review video if you would like, with examples and topics that will appear on the exam. That's important, right? And then the same breakdowns for the percentages, 20-minute video if you want the full 2.5%, all right? And just remember to make something new if you want that credit. Like, don't just like read over my slides or read over your answers to a lab or something. That's low effort. That's not extra credit worthy, okay? So just remember all that, and you should be good to go. Ask me if you have any questions. If you want to do this and you're not sure, like, is this a good enough idea? I will be happy to answer that before you spend time making a video. That is your extra credit assignment. Any questions about that? Let's see. And then we have a lab. Oops. We'll have a lab 2. but we'll deal with that next time, I think.